Okay, so this is going to be my last video on the camera tracker project because I've kind of run out of time to work on it anymore. So, but anyway, it's kind of like reached some sort of stage of completion, I guess. So, since the last video, I've migrated all the code off the laptop to the Raspberry Pi, which is underneath the camera base, and that's all wired up to the Arduino and some other interface stuff. So the whole thing is kind of like standalone. So I've got the thing actually mounted on a bike stand that I happen to like have in the shed. So it's really just a kind of like really beefed up tripod, because the only tripod I had was a very flimsy thing for only very lightweight cameras. So this actually works quite well and sort of stay up in the breeze. So so yeah, a very simple user interface on the setup. There's just like 4 LEDs that sort of illuminate in turn as you go through the setup process. So the first LED indicates that the Raspberry Pi is booted up, and you're kind of like set to set the initial camera orientation. So which you do with this little thumb joystick. So I can adjust the pan and the tilt, and there's a little button there. If I hold button down and press the joystick up and down, it actually sets the zoom of the camera via the LANC interface. So so once you've got the initial camera orientation set, so that's sort of with the camera pointing at where you're actually going to start your sort of filming from, you press the joystick button, and that kind of illuminates the second LED that indicates that the camera position set. The third LED will go on when it picks up the GPS lock from the tag. So I'm just going to go and get my tag and switch it on. Okay, so I'm filming inside, so I had to go and put the GPS tag over by the window so I could get a GPS lock. So anyway, it's got a lock now, so you can see now that the third LED has come on. So that means that it's picked up a GPS lock, like a 3D lock. So the next thing that you do is press just another button on the little joystick unit here to lock in the initial position of the camera unit. So you can see now that fourth LED is flashing. So what that means is that it's waiting for the GPS coordinates to settle. So it waits for the position to be steady before you do the next step. So it's just flashing for the moment, so it'll probably take a while to... There we go, it's just gone solid. So okay, so now what you would do, so that means it's recorded the GPS coordinates of the actual camera unit. The next step is you then take the tag over to where you're going to start filming from, and press a button on the tag to get the thing to start filming, which I'll... The new camera tag that I've sort of built. So this one's got an internal GPS antenna rather than the external one that I was using before, and it's all just in a little plastic jiffy box that I can put in a waterproof bag, which is kind of obviously what you need if you're going to take the thing out on the water. So it's just got on-off switch and this reset button here, which is what you press when you have gone to your initial camera filming location. And if I press the button, the camera does this nod thing, and what that is to give you some visual feedback that the camera has actually started recording, that it's picked up the reset button from the tag. So so there it is, sort of filming away. So getting some not very exciting footage of my lounge room. So anyway, so once you've finished and you want the the camera to stop recording, you switch the on-off switch on the tag, and obviously the camera will still keep filming at this point, but it'll stop moving because it's not getting any more GPS coordinates from the tag. And if I turn the tag on again, what that'll do is turn the camera off, so stop the recording, and turn the camera off, and return the servos back to their initial starting position, and also do a shutdown of the Raspberry Pi. So you can see now all the LEDs have gone off, so I'm now fine to like sort of hard power off the unit. So alright, now I'll take the thing off the tripod and give you a rundown of all the hardware that's underneath. Yeah, so here are some details on the hardware changes from the last prototype. So I ended up doing away, for the gimbal itself, I actually ended up doing away with the Lazy Susan bearing, because the main issue was trying to get the servo perfectly concentric with the bearing. So that meant that because it wasn't perfectly concentric, it meant there was some friction as the thing like rotated. So I've gone to the system now where the actual camera is sitting directly on top of a servo arm, but to provide some support and a little bit of friction, I've got these pins, which are basically nails with the head cut off, and a little plastic bead glued onto the end of it, and a little spring like underneath. So there are 3 of those, so that provides a twofold purpose, which is to provide some sort of support to stop the thing wobbling side to side, but also to provide a little bit of friction as the pan servo rotates. The reason for this is obviously this whole setup with the camera on it weighs quite a bit, so it has a reasonable moment of inertia. So without that, when the servo rotates to a particular position, it'll then oscillate backwards and forwards because it'll overshoot, and the servo will correct back the other way. So, but this setup seems to actually work quite well. So yeah, we'll tip the thing on its side now, and I'll show you all the electronics underneath. Okay, so here's the underneath of the unit. So the Python program that drives the whole thing is now running on this Raspberry Pi 0. So yeah, there was a little bit of fiddling required to get the whole thing sort of connected up, because the Raspberry Pi 0 just has the one USB port, and I didn't want to sort of have a USB sort of hub under here. So so in order to streamline things, I've actually got the actually soldered to the pins of the USB interface underneath the Raspberry Pi, and connected it up to this little board. So and did the same thing with the Arduino Uno. So the Raspberry Pi talks to the Uno via USB, but the connections are sort of soldered directly and connected via this little bit of perf board. So the perf board's also got the 7805 regulator on it, and so that's actually, the whole thing is powered by a 2-cell LiPo RC battery, which is like nominally 7.4 volts or whatever. So the 7805 regulator provides the 5-volt power supply for the Raspberry Pi. So the Arduino Uno is connected like directly to the 7.4 volt feed from the LiPo battery, because it's obviously got its own onboard power supply, and the 5 volts from that and 5 volts from the Uno is used to drive the servo driver board, and this other board here, which is just really some level interfacing stuff for the LANC interface, which is driven by the Uno. So So yeah, basically the way the whole thing works is the Raspberry Pi Zero sends serial commands via USB to the Uno, which controls all the hardware. So it controls the pan and tilt servos, and also the zoom on the camera, and also feeds back to the Raspberry Pi Zero the data from the joystick and the buttons. And yeah, the Uno also basically drives the LEDs. So the Python program then, obviously sends a command to the Uno to switch the LEDs on and off and reads the joystick positions, etc. Now the other thing that needed interfacing, I'll just tilt this back here, was the transceiver module, which picks up obviously the messages from the tag. So now with the previous setup, I had actually that, because that actually just provides TTL level serial at 9600 boards. It's pretty sort of pedestrian. So I did have that interfaced before via a serial to USB converter, which would plug into the laptop. And but obviously with the Raspberry Pi Zero just having the one USB port, I actually sort of pressed into service the serial port on the Raspberry Pi, which is available on from a couple of pins on the header, and that's normally used for a serial console for the Raspberry Pi for boot up messages and all the rest of it. So there's a little bit of configuring involved with the operating system to free that port up to be used to connect to the transceiver module. So, but that actually turned out to be relatively convenient, because that way it avoided the need for the USB to serial converter. So the Raspberry Pi actually powers the transceiver module by 5 volts from there, then actually goes up to the transceiver module, which is actually requires 3.3 volts. So that's what that little regulator board does there. That actually converts the 5 volts to the 3.3 that the transceiver module requires. So yep. So I'll take the lid off the tag in a sec and show you what's at the other end. Okay, so here's some detail of the hardware in the tag unit. So this is the second one that I've made. So the first one I used an Arduino Nano, which I happen to have in the shed. This time I've bought an Arduino Micro, which is even more sort of compact than the Nano. The main reason is it doesn't use a separate USB converter chip. But anyway, so that's just sitting on a bit of a prototype board, and I've sort of made the whole thing a little bit sort of 2D by mounting the NeoBlox GPS unit on a little header to raise it up, and then down the other end is the HMTRP transceiver module. So that's pretty much all there is to it. There's a couple of resistors and a Zener diode. So at the bottom there's a 2-cell LiPo battery that provides nominally 7.4 volts. That's powering the Arduino Micro, which has got its own onboard regulator, and then I use 5 volts from that to power the GPS unit. So the Zener diode is required because the transceiver module is actually 3.3 volt logic. So I've just got a resistor and a 3.3 volt Zener diode sort of powering that. So other than that, just an on-off switch and a reset button. So yeah, so the way the unit works is when you first switch it on, the GPS unit, the code on the Arduino sends absolute GPS coordinates back to the camera unit, and so that's required to actually absolutely set the GPS position of the camera unit, and also you need the absolute position of the position that you start off on. So when you press the button, what happens is the Arduino then ups the rate at which the GPS unit picks up coordinates, so it changes its from the default of 1 GPS reading per second to 4 per second, and then swaps to kind of like a different protocol for sending the coordinates. It then just starts to send deltas from the initial position that you started off on. So that's pretty much it. So yeah, so this unit's got a little sort of ceramic antenna. The other one I built used an external antenna, which is pretty handy for developing, because I could use the lead to put the GPS antenna outside, and so I could get a sort of GPS lock while I was actually working inside. So this unit all just fits in a jiffy box, and I've got some plastic bags that this can go in. So the idea was to obviously take it out on my stand-up paddleboard and maybe my RC boat and stuff like that. So I've kind of run out of time to do that, but I'm hoping to take the unit out of my RC boat tomorrow, but we'll see how we go.
So that's where I got up to with this project. A couple of days after the last footage was taken, I flew to Madrid for what was supposed to be a year-long trip. I never did get around to testing the setup with my RC boat or in the surf with my stand-up paddleboard. Anyway, I'm currently locked down in Portugal, awaiting a flight home to Australia. So to help pass the time, I finally got around to editing up this video. While I'm here, I'm going to try and finish a couple of other things, specifically draw up the circuit diagram and make up a parts list in fritzing. Also tidy up the Python and the Arduino code and upload it to a public repository, probably SourceForge, and start the build instructions ready to upload to instructables.com. The final version will have to wait till until we get home in May, as I can't measure the dimensions of any of the hardware because I don't have it with me. The next things I'm going to do when I get home is to do a bit more testing of just the current hardware. The main goal I had was actually to get out on my stand-up paddleboard with it and test it out in the water. Also, apart from that, I've been thinking of a couple of other sort of bits of hardware to experiment with. I am going to build another tag specifically for use with RC planes and my drone. The difference will be the tag will have a barometer sensor in it as well as the GPS. Because of the nature of GPS, the accuracy you get regarding altitude is only 1/3 that of latitude and longitude, whereas the barometer will provide a much more accurate reading for altitude, which will be pretty important if you're trying to sort of track a plane or a drone. I've also had an idea of using the actual camera gimbal hardware for another variation on this project. Obviously, because the current system uses a GPS, the unit won't work inside like at all. So there's a couple of commercial tracking units around that use actually an infrared sensor, that an infrared tag that the subject wears, and it tracks the infrared light. I'm sort of keen just to experiment with ultrasonics. Many years ago, I made mine interfaced a Nintendo Power Glove to a PC, and the Nintendo Power Glove actually used ultrasonic sensors to triangulate the position of the glove, and I was actually amazed at how accurately it worked. Also, the other factor is you can get ultrasonic sensors for Arduino Arduino boards very, very cheaply and easily. So so I thought it'd be fun to come up with a variation of the project that actually works inside. Anyway, that's about it. If you have any other suggestions as to other things I should try or other directions the project might take, let me know in the comments below. Otherwise, thanks for watching.